Okay, guys. I'm starting to cough a little bit. I don't know why. I think it's because when you don't talk a lot, like when you've been teaching, you work up these muscles, I guess, in your throat where you've been talking a lot. Now, I don't know. Anyway, so excuse me if I start coughing. All right, so this is showing you what happens if there's friction. We've been doing frictionless. Now let's talk about if we have friction. So if we have friction, then that's going to increase our thermal energy. Okay, so before we have initial and kinetic and potential, but now we're going to have final kinetic and potential, and we're going to add some thermal in there. Okay, because if you think about it, friction is going to make the surface, hot or add some of that heat. So your thermal energy is going to be greater than 0 in that case. So this is saying that the mechanical energy of kinetic and potential is not conserved if there's friction. And if you do the energy skate park simulation, you'll see that once you start to add the friction to it, you'll have to add the, you're actually going to have to try to figure out what the thermal energy is. Because all of this, right, all of that together should still equal that total energy. But that thermal energy, that friction is going to cause, that skater on the energy skate park simulation to slow down. So if you're watching this video and you haven't done the simulation yet, that might seem a little bit confusing because you don't know what I'm talking about. But once you get into it, hopefully that'll help to make sense of it a little bit. Okay. So this one is showing, this is saying a child that's on a playground swing, motionless at the highest point of his arc. What energy transformation takes place? My husband keeps texting me. This is what energy transformation takes place as he swings back down to the lowest point. So think about like a pendulum. You know that Newton cradle that I have in my classroom with all those metal balls, and you take the one and you hold it up and then you let go and it'll go through all of the balls and then push the other one on the other side up. That's called a Newton cradle, which is basically a pendulum. So here, if you have, let's say, here's the child is, let's say, at the tallest point right here. Okay, and they're swinging down, and it's saying, what is the energy transformation that takes place at the lowest point right here? Well, you could go and say, okay, between this point and this point right here, because this is like your highest point to the ground. So at this point right here, not that it stays, not that the swing stays there, it'll keep going this way. But at this point right here, does it have any potential energy? No, it does not. What about thermal energy? So let's think about that. At this point right here, could it have some thermal energy? Could it have any kind of friction involved? Well, it might not have kinetic friction. It could have some drag maybe, so you could kind of get into that a little bit. But we're not talking about in between either. We're talking about the slowest point. So what's the energy transformation? So from this point right here, it had total potential energy. So all these you can wipe out. And then at this point right here, it has total what? It has 0 potential energy and all kinetic energy. Okay? Now this one is saying that a skier is gliding down a gentle slope. So, they're going down like this. And let's say they started like maybe here. And they're going to here, but they're in between right now. So if they're in between, do they have potential energy still? Yes. Do they have kinetic energy still? Yes. What other kind of energy do you think might be taking place? Thermal energy, because there is some kinetic friction that's involved, okay? So this one's going to look more like this. At this point, you have started at potential and you're going You're going down the hill and you're creating thermal energy. Okay? So, all right. This is going back to elastic potential energy. We got into this somewhat. And this has to do with Hooke's Law. And now that I think about it, I didn't do the Energy Skate Park lab. I did the Hooke's Law lab. So you'll have the Energy Skate Park lab next week. So disregard everything I said on the previous slide when I was talking about the Energy Skate Park. Sorry. So this one's showing that you've got the figure shows a spring exerting on a force on a block, which we talked about that already. And this K you should know is that's the spring constant, which is telling you how rigid that spring is. And this delta S right here, that's how far it's displaced from its original position. So you can find the spring potential energy, which is this symbol right there, is equal to 1/2 K times the change of displacement squared. Okay, so definitely need your elastic potential energy equation. And going over here, and it says that a spring-loaded gun shoots a plastic ball with a launch speed of 2 meters per second. If the spring is compressed twice as far, the ball's launch speed will be what? All right, so let's set some stuff up really quick here. We're showing that you've got a speed, an initial speed right now of 2 meters per second. And it wants you to figure out what the ball's launch speed will be if you compress the spring back. So we're talking about speed, so we're talking about kinetic energy. And we're talking about springs, so we're talking about potential energy, but it's spring potential energy. So if you set these up, you've got something like this. Okay? Now, let's just kind of put some numbers in here, okay? So let's figure, like, if you've got V is equal to, and let's solve for V here. So if I take that times 2 to get rid of that 1/2, gets rid of the half over there. And then I gotta move my mass over like that, and then I've got this V squared, so I end up having to do the square root. I don't know why I wrote that so close. It's messing me up. Okay, so we've got V is equal to the square root of kx squared over m. Okay, so now I'm going to just plug some numbers in so that I get this initial speed to equal 2, because that's what it says the initial speed is. So if I take, let's say, and make the x 2, let's say I make k 1, and then I just do 2 squared over 1, and I do the square root of that, then I get 2. Okay? So that's good, because that's what I wanted for the initial speed. But this is saying if the spring is compressed twice as far, okay, so now I got to make my x twice as far. Okay, so let's keep everything else the same. So now I've got, now let's do 4 squared. Okay, so whenever you do that, you should get 4 meters per second. Shows you that you get D as your answer there. Okay, so hopefully that makes sense. Let's see, this next one, it says that a spring-loaded gun shoots a plastic ball with a launch speed of 2 meters per second. If the spring is replaced with a new spring having twice the spring constant, but still compressed the same distance, the ball's launch speed will be what? All right, so again, you kind of have to come up with some of your own, numbers. Same type of equation as before. So let's see, we have V is equal to the square root of kx squared divided by m. So let's get the initial speed to be 2 again. So plug in 1 and 2 squared over 1, and you end up with 2 meters per second. So what is the thing that has changed here? The distance is all the same, so this stays the same. The mass is all the same, so now we got to do V is equal to 2 times 2 squared divided by 1. So whenever you do that, you should get about 2.8 on your calculator. Okay? So that gives us answer C. All right. Oops. Come on. Okay, there we go. So now we're on if we're involving springs, okay, into this equation. So you can see this equation is starting to get rather long. So for a system that has gravitational interactions, so you've got potential gravitational energy, elastic interactions, so you've got some springs, and friction. So you're involving that thermal, but no external forces that do work. The energy principle is this mega, looking equation. So starting to get kind of long. And it even says that this is looking a bit more complex as we have more and more energies to keep track of. But the message is both simple and profound. For a system that has no other interactions with its environment, the total energy of the system does not change. So it can be transformed in many ways, but the total does not change. So we're still looking that we're going to have the same energy total, okay, which is this next slide that is saying, even if you have all of these things, the energy of the system should still remain constant and should still be this total amount of energy. All right. And this is just a picture that's showing it too, how they can all be transformed into one thing, and that the change of the energy is still, it's conserved. So anyway, that gets us to our next problem or example. So I'm going to stop the video here because I think this next one's going to take a little bit more time. Maybe not too much, but still, just in case.